Let's start today's lecture. Today we are going to study logical vectors. So we had a question in the tutorial about logical operations, and I hope everybody was managed to do that question. So today we are going to see what logical vectors are and what sort of operations we can perform on them. Logical vectors constitute a powerful and elegant feature native to MATLAB. When a vector is involved in a logical expression, the comparison is carried out element by element. And if the comparison is true, the element is given value 1. And otherwise, it is given a value 0. The same happens in logical expressions which involve matrices. So we have this simple example where R equals 1 to 5. Let's try this in MATLAB. So this is what we have in this vector, 1, 2, 3, 4, 5. Now if we write R less than equal to 3, then we are going to get a logical answer where when this expression is true, for those indices we are going to get a 1, and for the indices where this expression is false, we are going to get a 0. So it was where R is less than equal to 3. So for 1, 2, and 3, R is less than equal to 3. For the other two, R is greater than 3. Let's try the next one. B equals 0, 2, 3, 5, 6. Now what we are trying to do is that we already have the R vector, and we want to see for which indices R equals B. And as I mentioned a while ago, that we are going to see that when we compare these two vectors, the comparison is element by element. So this is what has happened. This was R. So R was 1, 2, 3, 4, 5, where B is 0, 2, 3, 5, 6. So for the second index, the value of R and B is equal. Therefore, we have got a 1 here. And then again, for the third index, the value of R and B is the same. We again got a 1 here. But for all the other indices in both R and B vectors, they are not equal to each other. That's why we get a 0. And you can also check the properties of X. So the name of this variable is X. The size is 1 times 5. There are 5 bytes. The class is logical, right? Logical means either you can get a value of 0 or 1. Now plotting the discontinuous graph. My apologies, this PDF is not working fine on this system. I'll try to upload a PowerPoint version, or I'll fix this because it was working on my system in my office. What we need to do is that we want to plot a graph y equals sine of x. and the values of x are between 0 and 3 pi. Okay, so here we have defined this x equals 0 to 3 pi with intervals of pi by 20, right? And y equals sine of x. However, we also want to set the negative values of y to 0. Okay, so this is how we do it here. When y is greater than 0, so when, let's say, y is 0.5, what would be the value of this logical expression? What would be the value of this logical expression? That would be true, 1. That would be 1, right? However, if the value of y is less than 0, what is going to happen? The value of this expression would become 0, right? So this, when this expression is 0, then the whole expression would become 0, right? And if this expression is 1, then this would be whatever the value of y. Okay, so we can now plot x versus y, and this is what we are going to get. And had we had not removed the negative values, then you would get a proper sinusoidal wave. But in this case, all the negative values are gone. Now, in this one, we want to avoid division by 0. So we are plotting sine function, sine x over x. However, let's have a look at the range of the function first. So it's between minus 4 pi to 4 pi with intervals of pi by 20. This is clear, right? This is how we can define this vector x. And then y equals sine of x divided by x. Now when x is 0, there is a problem. This is going to cause division by 0, and we would like to avoid this problem. So what we can do, remember the EPS function, what it does? So epsilon, what it would give you, see, it's going to give you the smallest value you can work with in MATLAB on your computer, right? So instead of dividing this thing by 0, which is going to give an error, we multiply it by this epsilon, which is this very small number. And how we are going to do this? So over here, we are checking a condition. Do you remember the difference between a single equal to and a double equal to? A single equal to is an assignment operator. And when you have two equal to signs, like we have in this expression, x equals to 0, then what we are doing? We are comparing the value of x with 0. And if x is equal to 0, what we are going to get? We are going to get a 1. Otherwise, we are going to get a 0. So let's assume that x is actually equal to 0. Then what is going to happen? We have gotten a 1, and this 1 will be multiplied by this epsilon, right? So instead of that 0, now this is going to get multiplied by epsilon. So what is going to be the value of x in this case? X equals, we have x plus x equal to 0 times epsilon. Where x is 0, this is 0. However, this expression x equals to 0 is going to be 1 multiplied by this epsilon. So we are going to get this new value of x. and then we can carry on with the rest of the calculation. There's another function which is plotting tan of x, and over here we want to avoid getting infinity as an answer. So we have the range of this function is between minus 3 pi by 2 to 3 pi by 2 with intervals of pi by 100. And y equals tan x, and we would like to plot this. Now it is impossible to see the structure since the very large values, those that are near plus minus 10 to the power of 16, they dominate, right? So we are going to add the following statement such that the values are the values which are too large, they get removed. Let's try this one on MATLAB. So x equals minus 3 times pi by 2 to, this is the step size, and then we have 3 times pi by 2. Fine. Y equals y equals tan x. We would like to plot. Now we are going to plot this function. Okay. So when the values of y are very large or very small, so you cannot really see the structure in the graph because of those values. So we'll try to get rid of them now. So what we do, we have already defined x, we have defined y, and now we are going to define a condition here, which is y times absolute value of y, it is less than 100. Okay, I forgot to put a semicolon this time. Now we are going to again plot this function, and we would get something like this, right? So the values of y are now no more than between 40 and minus 40, right? And now we can see a structure in this graph. And the important point was that this statement, this was kind of applying an if statement, right? Is this clear? Any questions so far? Okay. Now counting random numbers. So counting how many randomly generated numbers are less than 0.5. Let's see what happens in this example. So we have generated a very large number of random numbers, and then we apply a for loop. So the for loop starts from 1, n equals to 1, and it goes up to the length of r, because that's the number of random numbers that we have generated, and that are stored in r. So that's the length of r. And now we want to count the number. So whenever we are going to encounter a number that is less than 0.5, remember what is the range of the random function? It gives you numbers between 0 and 1, right? So whenever we have a number which is less than 0.5, we are going to increment this counter. This C is just a counter to find out that number. And that has nothing to do with whatever is going on in the for loop. So for your for loop, you have a different counter which runs from n equals to 1 to the length of r. Then we have got a timer as well here. With this function tick, the timer starts, and with talk, the timer stops. So then we can display the total numbers which are less than 0.5. Now we can code this in a different way. Doing the same thing with logical vectors requires, with logical vectors is more efficient and in terms of coding and computational effort. So how it is different? Similarly, we created this R vector, and it has random numbers. We start the timer. We stop the timer later, but the difference is in this particular line. Now, instead of that for loop and so many lines of code, we have a logical vector here. So whenever the sum of this whenever this logical vector is true, what is going to happen? That's going to get added into the sum, right? So it says sum r less than 0.5. Now you have this big array or vector of numbers. R has many numbers in it. Or let's say R has 0.5, 0.4, 0.3, and 0.7 and 0.8, right? 3, 4, 5, 4, 3, 7, 8, right? These are the numbers. Now what is going to happen is that whenever the value of that index is less than 0.5, those indices in the logical vector is going to get a 1, and we want to sum all of them. So that's how we can count the number of these random numbers which are less than 0.5 in this simple one line of code. That's clear? Any questions about this one? Now, logical operators. We did some logical operators a couple of lectures ago. Let's revisit them again. So we have these three operators, the main operators which we often use. The first one is not. This sign, the and sign is and the third one is or. MATLAB also has the exclusive OR relation implemented in the function XOR. So let's see what happens in these expressions if you apply logical operators. When we apply the NOT operator, so when we are applying an operation, we have an operator and something called an operand or a variable on which the operator works. So for a NOT operator, we only need a single variable. So when this is not expression 1, so what is the value of expression 1? False, or you can also say it's 0. So when it is not expression 1, then this value of false, this would become, see, this would become true. And for the rest of them, for the second one, false would become true. For the third one, true would become false, right? Now the next one is we take the AND of two expressions. So we have for the first line, for the first row, expression 1 and expression 2 both are false. And when we take AND of two zeros, what we are going to get? a 0 or a false. And then look at the second one. The first one is false and the second one is true. But for an AND operation, we are still going to get a, right? Because if I say that is today Tuesday and it's April, that's false, right? Look at the last one when both of them are true. So today is Tuesday and it's the month of March. So I use and here, and they both are true. So when both expressions are true, then the value of this one would be true. However, if we have an or here, what is going to happen? Either of the expressions could be true, right? So we are going to get a true, even for these two cases. Now, XOR is a little bit different. What is going on in XOR? When either both the expressions are true or both of them are false, we are going to get a false. And if one is true and the other is false, then we are going to get a true. Let's have a look at some of these examples. B square equals to 4AC, and A is not equal to 0. What's going to happen here? If this is true, that B square equals to 4AC, what we are going to get? A 1, right? And if A is not equal to 0, what we are going to get? Again a 1. Let me show this to you in MATLAB. Right, we have defined some random values. A equals to 1, B equals to 2, and C equals to 3. Now let's see what happens. So we have, this is B square. 2, 4A times C. A is not equal to right? Because B was 2. 2 times 2 is 4. And A is 1, C is 3. 4 times 3 is 12. Is 4 equal to 12? That's false, right? And then we have this AND operation over there, right? Let's see if we change this AND to OR. Now this would mean that if any one of them is true, we are going to get a true. See, the first was false, but the second expression, A not equal to 0, that's true. So we are going to get a true. So final is greater than or equal to 60 and final is less than 70. So whenever the value of this final is between 60 and 70, we are going to get a true. And if A is not equal to 0, or B is not equal to 0, or C is not equal to 0, so even if one of them is not equal to 0, you will get a true. The next one, let's see how it works. We already have the values of A, B, and C, which are 1, 2, and 3 respectively. None of them is a 0. What are we going to get here? True or false or what? A equal to 0, this is true, and b equal to 0. Sorry, this is false. A is not equal to 0, right? And c equals to 0. Is this the one? Oh, sorry, that's a not sign. That's fine. That's a not sign. Sorry, yeah, that's fine. Okay, that's fine. I need a not sign outside. Yeah, and c equals to 0. Okay. So, is a equal to 0? No. Is b equal to 0? Is c equal to 0? No. But in the end, we have a not sign. So, we're going to get it true. Although that, apart from the not sign, the whole expression evaluated to 0. But because of the not, we are going to get a 1. Not 0 and 0. And look at 5 and 6. What's the difference between both of them? Yeah, the first, not 0 and 0. Not 0 and 0. So not 0 would become, this is basically 1, and 0, this would be 0. And look at this, the sixth one, 0 and 0 is 1, and if we take a not of that one, that would be 0 again. Number 6, 7, and 8 are similar to the ones in tutorial. So you can solve them and try to fix them as well. So the precedence of logical operators. Now, first of all, brackets are evaluated, then the power or transpose, then the logical not, then multiply, divide, and matrix divide. After that, addition, subtraction, then the colon operator, then other relational operators, and then and or. So what does the following evaluate to? 2 is greater than 1 and 0. So what is the precedence? So first, this would be evaluated. 2 is 2 greater than 1. So this would be evaluated to true. And 0. So what is the answer? 0. So you can try others as well. Now logical operations on vectors. So logical operators can also operate on vectors and matrices. For instance, in the following case, we have this vector here, and in this expression it would replace all the non-zeros by ones and leave the zeros untouched, right? So zeros would remain untouched. However, these expressions which are not 0, they would become zeros. And you can try it here. Let's try it here. This one. So first we try this. Let's say a equals only this part. Minus 4, 1, 2, 0, minus 4, and we have another 0 then. Okay. So this, what happened here? I have tried it without the first bracket. A equals this array, and we have a not sign here, right? When we have a not sign, this means that whatever is this 0, that would become 1, and whatever is not a 0, that will become a 0. Okay? And then if I write the full example where I apply another not. So this is what is going to happen, that this all the non-zeros are, this replaces all the non-zeros by ones. This is what we saw that happen, and the zeros would remain untouched because you're applying kind of a double knot here. For clarity, brackets should be used to separate operators. That is, try avoiding doing this. Now, logical operations on vectors. So you can work this out. We'll do a couple here, and you can do the rest at home. A equals -1, 0, and 3, and B is 0, 3, 1. So what is the knot of A? What it would be? 0, 1, 0. Let's see if this is true or not. Equals -1, 0, and 3. And then we have the knot of A, which is 0, 1, 0, right? What happened was that you have taken the knot of this, right? And then you have A and B. So what would be the answer of A and B? B equals 0, 3, 1. Okay, and the AND of A and B is 0, 0, 1. So why this has happened here? Because we have an element-wise comparison, right? And only 3 and 1, they are true here because they are non-zeros. Whatever is a 0 here, consider it as holds, and whatever is non-zero here, that's true. So only the last two indices are true, and they would then give you a 1 here. You can apply rest of the operations at home. Do you want me to apply any one of these here now? Okay. Now, subscripting with logical vectors. So elements of a vector may be subscripted, referenced with vectors. For instance, you have A equals 2, -2, 0, 1, 5, and 9. Now you want to have a look at a subset of this vector A, right? So what you do is that you want the 5th, 1st, and the 3rd index, okay? And how you are going to refer to it? By putting the round brackets. And this is going to return 9, -2, and 1, because on the 5th index we have 9, on the 1st index we have -2, and on the 3rd index we have 1. We can also use logical vectors for subscripting, and you need to use this keyword there, right? So for instance, in this one, A logical 0, 1, 0, 1, 0, and what is going to happen here? We have asked MATLAB to return us the 2nd index and the 4th index, and nothing else. Okay, that's why we got 0, which is at the 2nd index, and 5, which is at the 4th index. What do the following statements return? What about the first one? Which indices do we want? First 3, right? So we are going to get -2, 0, and 1. And in the second one, which ones are we looking for? None. We don't need any one. Okay. Now in this one, x equals to logical 0, 1, 0, 1, 0. This is going to create a logical vector. This is how it would create a logical vector. X equals logical 0, 1, 0. so we are going to get a logical array. So for subscripting to work, the logical vector must be of the same length as the source vector, and the elements corresponding to the ones in the logical vector, they are going to be returned. So let's have a look at this example. So we have this vector A, which is -2, 0, 1, 5, 9, and then we have this index vector. Now we have done something wrong here. Yeah, we can see all zeros and ones, but is this a logical vector? What did we miss? Yeah, so we missed that logical keyword here. So you can also check whether a vector is logical or not by, you have this function here, let me write the vector first. So we have this index variable here, and we want to check whether this is logical or not, so we have this function called isLogical. So this is not logical, okay? And then we make it a logical one by writing this keyword here. Now let's try to check whether it's logical or not. Now it's a logical vector. And in this particular case, we are interested in the second and the fourth index, so we would get 0 and 5. The usefulness of logical vector subscripting stems from using logical expressions to perform subscripting. For example, in this one, A equals A and A is greater than 0. So it removes all positive elements of A. And if you have A equals A is greater than pi, that would remove all elements that are less than pi. So we had A here. This is our A, and we have A equals greater than 0. So this is what has happened, right? So anything which was greater than 0, we got it there. Okay. In this expression, the last one, A is less than 0 or A is greater than 5. So what is going to happen? Let's define a new A. A equals -1, -2, 0, 3, 5, 6, 7. Okay, so for this one, we have two conditions. The first one is A is less than 0, right? That's the first condition. Or A is greater than 5. So this would work for anything when where A is less than 0 or A is greater than 5. So you would get -1, -2, 6, and 7. But you're not going to get 0, 3, and 5. The reason being, 0 is not less than 0, and for these two ones, 3 and 5, they both are not greater than 5. So we have some of these logical functions. Any x, it returns 1 if any element of x is non-zero. So any of A, see, we had many elements which were non-zeros, right? That's why when we apply the any function, we got a 1. It's just a single answer. Now what about all x? So, okay. We are going to get a logical 1 for this one. And then find x returns a vector containing the subscripts of the non-zero elements of x. Thus, so for instance, we have x equals to 8, 1, -4, 8, 6. And you want to find the indices where the value of x is maximum. So what is the maximum value of x here? 8, right? And on which indices do we have 8? 1 and 4, right? So we are going to get 1 and 4. The next one is empty returns 1 if x is an empty array? Is INF returns 1s for the elements of x that are plus minus infinity? And is NaN, which means not a number, it returns 1 for the elements of x that are not a number. So we can use these any and all in if statements. So execute something, all elements of A are greater than 1. So if all are greater than 1, right, you can perform any operation. Say A equals 3, 4, and 5. Right? Now, all elements of A are greater than 0. Yeah. So if, okay, so we have this, if all A is greater than 1, this is our condition, not A is greater than 1, then display this. This one, and then we have an end here. So we saw that everything here was greater than 1, and we get to perform something within the if statement. Similarly, execute something if all elements are equal with the equal to sign, and you can apply other operations as well. For instance, in this one, any A is not equal to B. So you have two vectors and you are doing a comparison which is element by element. So whenever A is not equal to B for any of them, your if statement would be true, and you can perform something within the if statement, right? So it is wrong to test if A is not equal to B. Let's see what's the difference. A equals 1, 2, and 3, right? A equals 4, 5, and 3, let's say. So in the first one, one of them is true, but let's see if any A equals to B. Display hello here. I've missed. Okay, I'm not working with the not sign. I'm working with this one. You can try the not one at home. Now what happened in this one, let's say if any A equals to B, so over here A, this index and these were equal, right? But let's say if we do something a little bit different, if instead of any we do if A equals to B, then we are we cannot execute whatever is inside the if statement, right? Okay. Now using an else if ladder for taxes, so we have worked a lot with interest. Let's do some stuff with taxes. So if it's a very simple schedule here, where if the taxable income is less than 10,000, then 10%, then the tax payable is 10% of the taxable income. So if the taxable income is 10,000, then the tax would be 10%, 1,000. Okay. If it is between 10,000 and 20,000, then there is a constant amount of $1,000 plus 20% of the amount which exceeds $10,000. Okay, that would be taxable. And then if it is more than $20,000, then there's a fixed amount of $3,000 plus 50% of the amount by which the taxable income exceeds $20,000. Okay. So we can use an if-else ladder for taxes. So those are different incomes in the INC variable. And so we are going to run this loop for all the values which are there in that vector. So if the value of TI is less than 10,000, the tax was 10% times the income, which is 0.1 times the income. Else if it is less than 20,000, then 1,000 plus 20 times the income. Otherwise, it was 3,000 plus 50% of the income, which is greater than 20,000. And then you can display the income and the tax. So this is a simple if-else ladder to calculate taxes. You have done a couple of questions like this. In fact, in the tutorial as well, you calculated the amount of your electricity bill depending upon how much electricity you have consumed. Now what we can do is that we can replace the else if with logical vectors. So we have these salaries in this variable. That's fine up till now. And then how we are going to calculate the tax? So if the income is less than equal to 10,000, this expression would be evaluated to 1 if this is true. Then you would just multiply the 10% by the income and by 1. However, if the income is greater than 10,000, then this expression would be 0. So up till now, we can say, okay, if the tax is 0, let's execute the next statement. So this would be if the tax is greater than 10,000 and if the income is greater than 10,000 but less than 20,000. This would be true if the income is between 10 and 20,000. Right, or if then you are going to multiply it by 0.2 plus 1,000. And in the third one, if the income is greater than 20,000, then you are going to multiply it with this amount plus the 3,000. And then you can display the income and the tax. So over here, this is being multiplied here, right? You just forget the 3 dots. So we studied the logical vectors today, and they are a very nice and efficient feature in MATLAB. They could be used for subscripting vectors and matrices. And if you start using them, you're going to find out that you can take a lot of benefit from these logical vectors. And in the next lecture, we are going to study matrices. Okay, thank you very much.